Hey everyone, and welcome. As a senior mentor to all of you future innovators, designers, and builders, I am absolutely thrilled to kick off today's explainer. I want you to bring your absolute best energy today, right from the jump, because we're stepping into a totally dynamic 3D workshop. We're going to uncover the invisible laws that actually govern structural integrity. Now, it doesn't matter if you're sketching out the next towering skyscraper, engineering a cutting-edge mechanical engine, or designing an innovative suspension bridge. Mastering particle equilibrium is your literal starting point. It's the foundation of everything. So let's dive right in and build that foundation together, shall we? Okay, so here's our blueprint for today. We're looking at 4 foundational tools to really bridge that gap between theoretical physics and your practical design work. First up, vectors and force systems. Second, we'll hit particle equilibrium essentials. Third is free body diagram mastery. And finally, we'll wrap up with real-world engineering applications. All right, let's get into section 1, vectors and force systems. So I want you to take just a second and try to visualize the hidden forces acting on literally every object around us. I mean, the gravity pulling you down into your chair right now, or the tension in the massive steel cables of a suspension bridge. Our goal here is to make the invisible visible, but to do that, we first have to speak the language of physics. Take scalars, for example. You know these. They're quantities with just a magnitude, just a simple number. Things like mass, volume, length. You can just add them up with basic everyday arithmetic. But the real game changer for us as engineers is the vector. Vectors like force, position, and velocity have a magnitude, sure, but they also have a specific direction in 3D space. You absolutely cannot just add them up with simple math. We actually have to account for exactly where they are pointing, using tools like the parallelogram law. Now, to handle these directional vectors without losing our minds, we resolve them. If you picture a 3D isometric grid, we can take a single, complex, angled force, represented by just one vector, and break it all the way down into highly manageable x and y components, or u and v axes, depending on your setup. By using Cartesian vector notation, we're basically stripping a diagonal force into its purely horizontal and purely vertical effects. Honestly, it's kind of like reverse engineering that parallelogram law we just talked about, and it is the absolute secret sauce to solving complex structural problems. Okay, let's see how sharply you're tracking with all this in our first knowledge check. I'm going to hit you with 3 rapid-fire questions. Take a split second, lock in your guess. Ready? Question 1. Which quantity has only magnitude but 0 direction? Is it force or mass? Yep, the answer is mass. It's a scalar. Question 2. What geometric law do we use for vector addition? You got it, the parallelogram law. And question 3. Breaking a vector up into its horizontal and vertical parts is called what? Exactly right. That is vector resolution. Awesome job. Let's keep this momentum rolling. Moving right along to section 2, particle equilibrium essentials. So mastering vectors naturally leads us right to the golden rule of statics, which is equilibrium. According to Newton's first law, equilibrium is a state where the resultant, or the net combination of all forces acting on a particle is exactly 0. Now listen closely to this part, because it trips up a lot of people. A resultant force of 0 means the particle will remain totally at rest, or, and this is a big or, it will continue moving at a constant speed in a straight line. Equilibrium is all about a state of perfectly balanced forces. It does not necessarily mean just sitting completely stationary. Let's put that into perspective. Consider a particle being pulled by a 100-pound force straight up and a 100-pound force straight down along the exact same line of action. Because they have equal magnitude but opposite sense, they perfectly cancel each other out. And hey, we see this in everyday life all the time. Think about a heavy textbook resting on a table. The downward weight of that book is perfectly balanced by the upward reaction force, what we call the normal force of the table pushing back. The rightward forces perfectly balance the left. The upward forces balance the down. The net effect is 0. That, my friends, is equilibrium. Time for knowledge check number 2. 3 quick questions to really lock in Newton's first law. Question 1. If the resultant force on a particle is 0, what specific state is that particle in? Answer is equilibrium. Question 2. What's the term for the vector combination of all forces acting on a body? We call that the net force, or the resultant force. Question 3. True or false? An object moving at a constant velocity with 0 acceleration can actually be in equilibrium. The answer is true. Equilibrium just means balanced forces, even if the thing is in uniform motion. All right, section 3, free body diagram mastery. It is officially time to translate the messy, chaotic physical world into clean, elegant engineering math. And we do this using our single most powerful visual tool. Take a look at a typical physical scene. We call this a space diagram. It's basically a sketch showing the real-world physical conditions of a problem. So imagine a massive 3,500 kilogram automobile being unloaded from a cargo ship. It's supported by this heavy crane cable, while the worker on the dock pulls on a rope to center it. It's a very real-world, very messy environment. But as engineers, we can't exactly do precision math on a drawing of a truck and some buildings, right? We need to completely strip away this physical environment so we can see the raw underlying physics at play. To do that, we follow 3 strict, non-negotiable steps to create our free body diagram. This strips away the background noise to leave only the pure mechanics. Step 1. Isolate the particle. We basically just choose the exact junction point where all the ropes meet. Step 2. Identify all applied forces acting on that specific point, so the weight pulling down and the tensions from the cables pulling up and off to the side. Step 3. Draw and label the vectors. Here's where we apply our Cartesian logic to show exactly where these forces are pointing and exactly what magnitudes they have. Let's see how this all comes together to build our final free body diagram. Notice how we have completely removed the car, the ship, the buildings. The whole physical world is gone. We literally just have point A, our downward weight vector, and our 2 tension vectors acting at their specific angles. From there, we can easily create a force triangle. If we draw these vectors tip to tail and they form a perfectly closed polygon, boom. That graphically proves that our net force is 0 and our entire system is sitting in perfect equilibrium. All right, let's test your retention with Knowledge Check 3. Question 1. What's the main difference between a space diagram and a free body diagram? Answer. A space diagram shows the messy physical environment, while an FBD strips all that away to show only the selected particle and the forces acting on it. Question 2. What is the very first step in drawing an FBD? Answer. Isolate the particle. You gotta separate it out. Question 3. If you draw 3 forces tip to tail and they happen to form a closed triangle, what does that prove? It proves your system is in equilibrium. And now for our final part, Section 4, Real-World Engineering Applications. Okay, so we've mastered the theory, we've learned the tools, and now we're going to put these diagrams to the ultimate test on some actual engineering problems. Imagine you're tasked with designing a heavy traffic light system for a super busy intersection. Think about a traffic light hanging from 2 angled steel cables. Gravity is just relentlessly pulling that heavy light downward. As the engineer in charge, you have to figure out how that downward weight must be perfectly counteracted by the upward tension in those 2 specific cables, because obviously, if those cables fail, the light crashes into the street. So how on earth do we calculate the exact strength needed for those cables? Well, we turn it right into a free body diagram. When we map out the vectors for the tension in each cable and resolve them into their Cartesian components, we see something honestly pretty beautiful algebraically. The horizontal pole of the left cable perfectly cancels out the horizontal pole of the right cable. They are totally equal and opposite. This means they're out of the equation entirely, leaving only the vertical upward components of both cables working perfectly together to balance the downward weight of the traffic light. The net force is 0, equilibrium is officially achieved. Now let's look at something a bit more complex, a real hydrodynamic scenario. Imagine a prototype sailboat hull in a water test channel being held perfectly in place by 3 cables against a fast flow of water. Now let's say we know the tension in 2 of the cables is 40 pounds and 60 pounds. By simply isolating the bow of the boat as our single particle and drawing our free body diagram, we can use those known cable tensions and a little bit of trigonometry to geometrically determine the exact invisible drag force the water is exerting on the hull. This right here is exactly how engineers calculate huge forces that cannot be easily seen or measured. All right, here is our final rapid-fire quiz, Knowledge Check 4. Question 1. In our hanging traffic light example, what actually balances the downward weight? Answer. The vertical upward components of the tension in those 2 cables. Question 2. In the sailboat hull test, what specific force are the cables counteracting? Answer. The invisible drag force of the water. Question 3. What mathematical tool do we use to solve for these unknown tensions in our free body diagrams? Answer. Good old Cartesian vector logic and trigonometry. Well, look at that. You've officially mastered scalars, vectors, Newton's first law, and the all-important free body diagram. You now possess the analytical tools to actually see the invisible forces that are literally holding the physical world together. So I want to leave you with this final thought. How will you apply these invisible laws of equilibrium to design the groundbreaking structures of tomorrow? The blueprint is entirely in your hands now. keep calculating, keep questioning everything, and keep building. Thanks so much for learning with me today. I'll catch you next time.